Chapter 11 Three-dimensional geometry. We are going to learn about planes. Definition of a plane is a flat two-dimensional surface that extends infinitely. We usually draw planes with edges, but really they don't have edges. Let us consider a point. It has 0 dimension. Consider a line. It has 1 dimension. Consider a plane. It is a two-dimensional figure. Now, for example, let us take a cube. It is a three-dimensional figure. A point has 0 dimension, line has 1 dimension, and this has 2 dimensions, and cube has 3 dimensions. Let us see some properties of planes. If you consider two planes, either they should be parallel or they have to intersect along a line. And this is the line of intersection. We don't have skew planes in 3D. Let us consider a plane and a line. The line may be parallel to the plane, or the line may intersect the plane at a point, or the line may completely lie on the plane. Next, let us consider a plane and two lines perpendicular to this plane. Let this be one line which is perpendicular to this plane, and let us draw another line perpendicular to the same plane. Then these two lines should be parallel to each other. Therefore, two distinct lines perpendicular to the same plane are parallel to each other. Now let us consider a line and let us draw two planes parallel to this line. Then these two planes should be parallel to each other. A plane is uniquely determined in the following cases. The first one, the normal vector and distance of the plane from the origin are given. Any vector that is perpendicular to the plane is called the normal, and this is called the normal form of a plane. The second one is a point on the plane and normal to the plane are given. And the third one is when three non-collinear points lying on the plane are given. Let us see the formulae of planes in these three cases. Let us see the first case, equation of a plane in normal form. Let us consider a plane. Let O be the origin. Draw a perpendicular OL to the plane, and P be an arbitrary point on the plane, whose position vector is vector r. So vector OP is vector r. Let us join P and L, where L is the foot of the perpendicular, and vector n cap be a unit normal vector to the plane. If P is the distance of the plane from the origin, then OL vector can be written as P n cap. Distance of the plane from the origin is P, which is OL, and OL is parallel to n cap. Therefore, vector OL is equal to P n cap. LP vector, LP lies on the plane. Therefore, LP vector is position vector of the terminal point minus position vector of the initial point. So I will write that vector here in the figure, r minus p times n cap. Now LP is perpendicular to n cap because LP lies on the plane and n cap is perpendicular to the plane. Therefore, dot product has to be 0. R minus p n cap dot n cap should be 0. Dot product is distributive over subtraction. Therefore, vector r dot n cap minus p n cap dot n cap is equal to 0. Vector r dot n is equal to p, n dot n is 1, where p is the distance of the plane from the origin. This is the vector equation of a plane in normal form. Let us write the Cartesian equation of this plane. We will take vector r as xi plus yj plus zk, and n cap, it is a unit vector. So we can write it in terms of direction cosines lmn. So n cap is equal to li plus mj plus nk. Vector r dot n cap, let us do the dot product and write. Multiply the corresponding components. Lx plus my plus nz is equal to p, where p is the distance of the plane from the origin. This is the Cartesian equation of the plane in normal form. Second case, let us derive the formula of a plane when a point and normal vector of a plane are given. Consider this plane. Let n be the normal vector. In this case, it need not be a unit normal vector. Let a be the point on the plane which is given, whose position vector is vector a. Vector OA is equal to vector a, which is given, and normal vector is given. Let us take an arbitrary point P on the plane, whose position vector is vector r. Let us join A and P. Vector AP is equal to terminal point minus initial point. So it will be vector r minus vector A. And vector AP is on the plane, and vector n is perpendicular to the plane. Vector AP is perpendicular to vector n, therefore dot product has to be 0. And vector AP is vector r minus vector A. Dot n is equal to 0. Let us distribute. We get r dot n minus A dot n is equal to 0. Therefore, vector r dot vector n is equal to, we will take A dot n as d. This is the vector equation of a plane when you know one point and normal vector to the plane. And it can be reduced to r dot n is equal to d form. Let us write the corresponding Cartesian equation of this plane. Let vector r be xi plus yj plus zk, and the given point vector a be x1i plus y1j plus z1k. Let vector n be ai plus bj plus ck, where a, b, c are the direction ratios of the normal. Let us substitute in the vector equation. R minus a will be x minus x1i plus y minus y1j plus z minus z1k. Dot vector n is ai plus bj plus ck and equal to 0. Let us do the dot product. A times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. This is the Cartesian equation of a plane when you know one point and normal vector to the plane. Let us open the brackets and simplify this equation. Ax plus by plus cz minus ax1 minus by1 minus cz1 equal to 0. Ax1 minus by1 minus cz1 is the constant term. Ax plus by plus cz is equal to d, where d is the constant term. Therefore, the plane equation is a linear equation in x, y and z. Now the third case. Let us derive the equation of a plane passing through three non-collinear points. Let us consider this plane on which three points are given, A, B, C, whose position vectors are vector A, vector B and vector C respectively. Remember, to write the equation of a plane, we need a point on the plane and normal vector to the plane. If normal is not given, we have to do cross product of any two vectors which are on the plane or parallel to the plane. To find the normal vector, we will get two vectors which are on the plane. Let us join AB and AC. Vector AB is vector B minus vector A, and vector AC is vector C minus vector A. If we do the cross product of these two vectors, it will be perpendicular to the plane, which can be taken as the normal vector. Therefore, vector n is B minus A cross C minus A. Let us take an arbitrary point P on the plane, whose position vector is vector r. That is, vector OP is vector r. Let us join OA. OA is vector A. Join AP. Vector AP is equal to terminal point minus initial point. Therefore, we get vector r minus vector A. Vector AP is perpendicular to vector n because vector AP lies on the plane and vector n is perpendicular to the plane. Therefore, dot product has to be 0. Vector r minus A dot vector n is equal to 0. Let us substitute for vector n. Vector r minus vector A dot vector n is B minus A cross C minus A equal to 0. This is the vector equation of a plane passing through three non-collinear points. Let us write the corresponding Cartesian equation of this plane. Let us take vector r as xi plus yj plus zk and vector A as it's a point x1i plus y1j plus z1k, position vector of A point, and vector B as x2i plus y2j plus z2k, and vector C as x3i plus y3j plus z3k. Left hand side of this equation has dot and cross, which is a scalar triple product, and it can be written as a determinant. Determinant vector r minus vector A is x minus x1, y minus y1, z minus z1, and the second row is B minus A, x2 minus x1, y2 minus y1, z2 minus z1, and the third row is vector C minus vector A, x3 minus x1, y3 minus y1, and z3 minus z1. And don't forget to write equal to 0. This is the Cartesian equation of a plane passing through three non-collinear points. The general form of a plane equation is ax plus by plus cz plus d equal to 0, or we may write equal to d. If d is equal to 0, then this plane passes through the origin. If d is not equal to 0, then the plane doesn't pass through the origin. Let us consider this plane intersecting the three coordinate axes at P, Q, R respectively on x, y and z axes. P point is A0, 0. Let Q point be 0, B0 and R point be 0, 0, C. Let us substitute P point A0, 0 in this plane equation. We get AA plus D equal to 0. Therefore, A is minus D divided by A. Next, let us substitute Q point, which is 0, B0. We get B plus D equal to 0. Therefore, B is minus D by B. R point is 0, 0, C. Let us substitute in the equation. C plus D is equal to 0. Therefore, C is minus D by C. Let us substitute all these three values of a, b, c in the plane equation. We get minus d by a x minus d by b y minus d by c z plus d equal to 0. Let us divide the whole equation by minus d. X by a plus y by b plus z by c. We will get minus 1. We will take it to the other side, so plus 1. This is the intercept form of a plane equation, where a, b, c are the intercepts made by the plane on x, y, z axes respectively. If the plane equation is ax plus by plus cz plus d equal to 0, then the coefficients of x, y, z are the direction ratios of the normal. Very important point you should remember. From the equation of the plane, the coefficients of x, y, z are the direction ratios of the normal. Using these formulae, let us do the first 8 questions of exercise 11.3 and then we will learn the rest of the formulae. First question. In each of the following cases, determine the direction cosines of the normal to the plane and the distance from the origin. A subdivision, the equation is z is equal to 2. The coefficients of x, y, z are the drs of the normal. Here coefficients of x and y are 0 and 0. Therefore, drs of the normal are 0, 0, 1. Let us find the dc's of normal. We have to divide by the magnitude. The magnitude here is root of 1 square, which is 1. Therefore, dc's are also 0, 0, 1. The equation is already in the normal form. The normal form is Lx plus My plus Nz is equal to P, where P is the distance of the plane from the origin and P has to be a positive quantity. Therefore, distance of the plane from the origin is 2. Now the second subdivision. The equation is x plus y plus z is equal to 1. The coefficients of x, y, z are the drs of the normal, which are 1, 1 and 1. Let us find the dc's. We have to divide by the magnitude of this normal. Let us find the magnitude, which is root of 1 plus 1 plus 1, which is root 3. Let us divide by root 3. So dc's are 1 by root 3, 1 by root 3, 1 by root 3. Now we will divide the whole equation by root 3. We get 1 by root 3x plus 1 by root 3y plus 1 by root 3z equal to 1 by root 3. Keep this constant term on the right hand side as a positive quantity. This equation is in normal form. Lx plus my plus nz is equal to p, where p is the distance of the plane from the origin, which is 1 divided by root 3. Now subdivision C. The equation is 2x plus 3y minus z is equal to 5. The drs of the normal are the coefficients of x, y, z, which are 2, 3, minus 1. Let us calculate the magnitude of this. Root of 4 plus 9 plus 1, which is root 14. Let us divide the whole equation by root 14. 2 divided by root 14x plus 3 divided by root 14y minus 1 divided by root 14z is equal to 5 divided by root 14. Keep the constant term on the right hand side as a positive number. We have written this equation in normal form. Therefore, the dc's of the normal are 2 by root 14, 3 by root 14, minus 1 by root 14. Only when the equation is in the normal form, the coefficients of x, y, z are the dc's of the normal. In this equation, the coefficients are drs of the normal. Therefore, distance of the plane from the origin is 5 by root 14. Next, D subdivision. 5y plus 8 is equal to 0. Let us write the coefficients of x, y, z, which are the DRs of the normal. 0, 5, 0. X and z terms are not there. Magnitude of this is root of 5 square, which is 5. We will divide the equation by 5 to change it to normal form. We get y plus 8 divided by 5 is equal to 0. Therefore, minus y is equal to 8 by 5. And this number represents the distance of the plane from the origin. It has to be a positive quantity. That's why I have written the minus sign on the left hand side. Let us write the DCs of the normal. The above equation is in the normal form. Only when the equation is in normal form, the coefficients of x, y, z will give the DCs of the normal. Coefficient of x is 0, coefficient of y is minus 1 and coefficient of z is 0. Therefore, the distance of the plane from the origin P is equal to 8 by 5. DCs of the normal can be written by changing the sign also. It can be written as 0 plus 1 and 0. Question number 2. Find the vector equation of a plane which is at a distance of 7 units from the origin and normal to the vector 3i plus 5j minus 6k. Distance of the plane from the origin is given as 7, that is P is 7. Since this distance is given, we will use normal form of the plane equation. And vector n is given as 3i plus 5j minus 6k. The vector equation of a plane in normal form is vector r dot n cap is equal to p, where n cap is the unit normal vector and p is the distance of the plane from the origin. We will change vector n to n cap by dividing by its magnitude. 3i plus 5j minus 6k divided by its magnitude is root of 9 plus 25 plus 36. We get 3i plus 5j minus 6k divided by root 70. Let us substitute n cap in the equation. We get vector r dot 3i plus 5j minus 6k divided by root 70 is equal to 7. Or we may take root 70 to the other side and write it as vector r dot 3i plus 5j minus 6k is equal to 7 times root 70. Question number 3. Find the Cartesian equation of the following planes. The first subdivision, vector r dot I plus j minus k is equal to 2. So easy to change it to Cartesian form. We have to just substitute vector r as xi plus yj plus zk. Dot I plus j minus k is equal to 2. Let us do the dot product. X plus y minus z is equal to 2. This is the Cartesian equation. Remember, in Cartesian equation of a plane, x, y, z are the variables, which is taken as vector r. Without x, y, z, we cannot write a Cartesian equation. Similarly, without vector r, we cannot write a vector equation of a plane. B subdivision, vector r dot 2i plus 3j minus 4k is equal to 1. We know that vector r is xi plus yj plus zk and dot 2i plus 3j minus 4k is equal to 1. Let us do the dot product. We get 2x plus 3y minus 4z equal to 1. This is the Cartesian equation of the plane. Subdivision C. The given equation is vector r dot s minus 2t I cap plus 3 minus t j cap plus 2s plus t k cap equal to 15. Same method, we will substitute vector r as xi plus yj plus zk dot s minus 2t I cap plus 3 minus t j cap plus 2s plus t k cap equal to 15. Let us do the dot product. No ijk in the dot product. We get s minus 2t times x plus 3 minus t times y plus 2s plus t times z is equal to 15. This is the Cartesian equation of the plane. Question number 4. In the following cases, find the coordinates of the foot of the perpendicular drawn from the origin. The equation of the plane given is 2x plus 3y plus 4z minus 12 equal to 0. Let O be the origin and L be the foot of the perpendicular. Direction ratios of the normal are the coefficients of x, y, z, which are 2, 3 and 4. Remember, to find a point, always write that point in terms of lambda using the line equation on which it lies, and L lies on OL. Let us write the equation of the straight line OL. The formula is x minus x1 divided by A equal to y minus y1 divided by B equal to z minus z1 divided by C. x1, y1, z1 is a point on the line, which is the origin in this case. The coordinates are 0, 0, 0. Let us substitute x minus 0 divided by 2 equal to y minus 0 divided by 3 equal to z minus 0 divided by 4. We will equate this to lambda. Any point on this line will have the x coordinate 2 lambda, y coordinate 3 lambda, z coordinate 4 lambda. L also lies on this line. Therefore, L will be of the form 2 lambda, 3 lambda and 4 lambda. To find lambda, we have two methods. One is substitution method, the other one is perpendicularity method. Here L lies on the plane. So let us substitute L in the plane equation. We get two times 2 lambda plus 3 times 3 lambda plus 4 times 4 lambda minus 12 equal to 0. 4 lambda plus 9 lambda plus 16 lambda, let us take 12 to the other side, equal to 12. Here the total is 29 lambda is equal to 12. Therefore, lambda is 12 divided by 29. Therefore, the point L, which is the foot of the perpendicular from the origin, is 2 lambda, which is 24 by 29, 3 lambda 36 divided by 29 and 4 lambda 48 divided by 29. Next, B subdivision. The equation is 3y plus 4z minus 6 is equal to 0. Let O be the origin, whose coordinates are 0, 0, 0, and OL is a perpendicular drawn to the plane. L is the foot of the perpendicular. Any perpendicular line can be taken as the normal. Therefore, drs of OL are the coefficients of x, y, z, 0, 3, 4. From the plane equation, we can write the drs. Now, let us write the equation of OL. The formula is x minus x1 by A equal to y minus y1 by B equal to z minus z1 by C. x1, y1, z1 is the point origin, which is 0, 0, 0. A, B, C are the direction ratios of the normal, which are 0, 3, 4. Therefore, we get x by 0 equal to y divided by 3 equal to z divided by 4. Let us equate this to lambda. Any point on this line can be written in terms of lambda. X coordinate will be 0 lambda, y coordinate is 3 lambda, z coordinate is 4 lambda. L also lies on this line. Therefore, L will be of this form 0, 3 lambda, 4 lambda. Now, to find lambda, we will substitute this L point in the plane equation because L lies on the plane. We get 3 times 0 plus 3 times 3 lambda plus 4 times 4 lambda minus 6, which is equal to plus 6. We will take it to the other side. Therefore, 25 lambda is 6. Lambda is 6 divided by 25. Therefore, the foot of the perpendicular L will be 0. 3 lambda is 18 divided by 25 and 4 lambda is 24 divided by 25. C subdivision. The equation of the plane is x plus y plus z is equal to 1. Let us draw a normal. Any perpendicular line can be taken as the normal. So, we are considering OL as the normal. O is the origin, coordinates are 0, 0, 0. Direction ratios of OL are the coefficients of x, y, z, which are 1, 1 and 1. Now, we will write the equation of the line OL. Let us write the formula. X minus x1 divided by A equal to y minus y1 divided by B equal to z minus z1 divided by C. x1, y1, z1 is the origin 0, 0, 0 and A, B, C's are the direction ratios of the normal, which are 1, 1, 1. Let us substitute. X minus 0 by 1 equal to y by 1 equal to z by 1. Let us take it as equal to lambda. Any point on this line will be of the form lambda, comma lambda, comma lambda. L also lies on this line. Now, to find lambda, we know that L lies on the plane. Therefore, we will substitute L point in the plane equation. Therefore, we get lambda plus lambda plus lambda is equal to 1. 3 lambda is equal to 1. Lambda is equal to 1 divided by 3. Therefore, the foot of the perpendicular from the origin to the plane, which is L, is the point 1 by 3, 1 by 3, 1 by 3. D subdivision. The equation is 5y plus 8 is equal to 0. Let us draw OL perpendicular to the plane. L is the foot of the perpendicular. O is the origin 0, 0, 0. Any perpendicular line is the normal to the plane. We can take the coefficients of x, y, z as drs of the normal. Coefficient of x is 0, coefficient of y is 5 and z coefficient is 0. Let us write the equation of the line OL. Remember, wherever we have to find a point L, we have to write it in terms of lambda using the line equation on which it lies. That's why we are writing the equation of OL. The equation is x minus x1 by A equal to y minus y1 divided by B equal to z minus z1 divided by C. Let us substitute x1, y1, z1 as 0, 0, 0 and ABCs as 0, 5, 0. We get x by 0 equal to y by 5 equal to z by 0 equal to lambda. Any point on this line OL will be of the form 0, 5 lambda and 0. L also will be of this form. To find L, let us substitute L point in the plane equation. Therefore, we get 5 times 5 lambda equal to minus 8. Therefore, lambda is equal to minus 8 divided by 25. Let us substitute this lambda value in L. Therefore, the foot of the perpendicular L is 0, minus 8 by 5, 0. Question number 5. Find the vector and Cartesian equations of the planes. The first one, that passes through the point 1, 0, minus 2, and the normal to the plane is I cap plus j cap minus k cap. It is an easy question because directly the point and the normal vectors are given, which we need to find the equation of the plane. The point on the plane is 1, 0, minus 2, and normal vector is given directly. If it is not given in the question, we do the cross product of any two vectors which are on the plane or parallel to the plane. The plane equation is vector r minus vector a dot vector n is equal to 0. Let us distribute. Vector r dot vector n is equal to vector a dot vector n. A and n are given. Vector r dot n vector is I plus j minus k, and vector a is the position vector of the given point 1, 0, minus 2. Therefore, it is 1i plus 0j minus 2k dot n vector is I plus j minus k. We will do the dot product. We get 1 plus 0 plus 2, which is 3. Therefore, the equation is vector r dot I plus j minus k equal to 3. We have to write the Cartesian equation also. It is easy to write the Cartesian equation. Directly we can write. We know that vector r is xi plus yj plus zk. Therefore, it becomes 1 into x plus 1 into y minus 1 into z equal to 3. This is the Cartesian equation of the plane. Now B subdivision. Find the vector and Cartesian equations of the plane that passes through the point 1, 4, 6, and the normal vector to the plane is I cap minus 2j cap plus k cap. And the point vector is 1i plus 4j plus 6k. Let us write the equation of the plane. This is also a direct question. Vector r minus vector a dot vector n is equal to 0. Let us distribute. Vector r dot vector n is equal to vector a dot vector n. Therefore, we get vector r dot n vector is I cap minus 2j cap plus k cap equal to vector a dot vector n. We will do the dot product of these two vectors directly. 1 minus 8 plus 6, which is equal to minus 1. Therefore, the vector equation is vector r dot I cap minus 2j cap plus k cap is equal to minus 1. Now we have to write the corresponding Cartesian equation. Let us substitute vector r as xi plus yj plus zk and find the dot product. We get 1x minus 2y plus 1z equal to minus 1. Question 6. Find the equations of the planes that passes through 3 points. So these 3 points should be non-collinear points. Let us see what happens if they are collinear points. Let us take 3 points which are collinear, A, B, C. Passing through these 3 points, we can draw infinitely many planes. Let us draw another plane passing through these 3 points. Similarly, we can draw infinitely many planes passing through 3 collinear points. Therefore, to find the equation of a plane, we need 3 non-collinear points. Now, A subdivision, the 3 points given are 1, 1, minus 1, 6, 4, minus 5, minus 4, minus 2 and 3. And we know the formula to write the equation of a plane. Determinant x minus x1, y minus y1, z minus z1. The second row is x2 minus x1, y2 minus y1, z2 minus z1. And the third row is x3 minus x1, y3 minus y1 and z3 minus z1. And equal to 0, don't forget to write equal to 0. Let us substitute. The first row is x minus 1, y minus 1 and z minus of minus 1 plus 1. We will take the first point as x1, y1, z1 and the second one as x2, y2, z2 and third one as x3, y3, z3. Therefore, the second row is second point minus first point, 6 minus 1, 5, 4 minus 1, 3, minus 5 and plus 1 is minus 4. Now, third point minus first point, minus 4 minus 1, minus 5, minus 2 minus 1, minus 3 and 3 plus 1, 4 equal to 0. Look at the second and the third rows, they are proportional. If you expand this determinant, you will get 0 equal to 0. Let us name these points as A, B, C. Therefore, DRs of AB proportional to DRs of AC. That means AB is parallel to AC. That means A, B, C are collinear points. So through 3 collinear points, we have infinitely many planes. In this case, we cannot find the equation of a plane. So write that A, B, C are collinear. Therefore, we have infinitely many planes passing through the given 3 collinear points. B subdivision, we will take the points as A 1 1 0, B 1 2 1 and C minus 2 2 and minus 1. Let us take the first point as x1 y1 z1, second one as x2 y2 z2 and the third point as x3 y3 and z3. Let us write the formula. X minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1 and the last row is x3 minus x1, y3 minus y1, z3 minus z1 and equal to 0. Let us substitute. X minus 1, y minus 1, z minus 0, second point minus first point, 0, 1 and 1. C minus A, minus 2 minus 1 is minus 3, 2 minus 1 1 and minus 1 equal to 0. Let us expand this determinant. X minus 1 times minus 1 which is minus 2 minus of y minus 1 times 0 plus 3 which is 3 plus z into 0 plus 3 which is 3 equal to 0. Let us open the brackets. Minus 2x plus 2 minus 3y plus 3 plus 3z is equal to 0. We get minus 2x minus 3y plus 3z equal to minus 5. Let us change the sign throughout. 2x plus 3y minus 3z is equal to 5. This is the plane equation passing through three non-collinear points. Now question 7. Find the intercepts cut off by the plane 2x plus y minus z is equal to 5. We know the intercept form of the equation of a plane. X by a plus y by b plus z by c is equal to 1. So we need 1 here. Let us divide the whole equation by 5. We get 2x divided by 5 plus 1 divided by 5y minus 1 divided by 5z is equal to 1. Let us write this equation in the intercept form. X divided by 5 divided by 2 plus y divided by 5 plus z divided by minus 5 is equal to 1. Therefore, the intercepts are 5 divided by 2, 5 minus 5 on x, y, z axes respectively. Question number 8. Find the equation of the plane with intercept 3 on the y-axis and parallel to ZOX plane. This is ZOX plane and its equation is y is equal to 0, because for all points on this plane y coordinate is going to be 0. Consider this plane passing through the y coordinate 3. Its equation will be y is equal to 3. We know that if two planes are parallel, only the constant term will be different. Equation of ZOX plane is y is equal to 0. So for parallel planes, only the constant term will be different. Therefore, equation of a plane with intercept 3 on the y-axis and parallel to this will be of the form y is equal to k. But here it passes through 3. Therefore, the answer will be y is equal to 3. Let us learn about the equations of planes passing through the intersection of two given planes. If you consider two planes in three-dimensional geometry, either they should be parallel or they should intersect each other. If two planes intersect each other, they intersect along a line. We denote the planes by the letters pi 1, pi 2, etc. So let us take this as the first plane pi 1, this as pi 2. They are intersecting along a line. Now through this line of intersection, we can draw infinitely many planes. Consider a notebook, open notebook with pages. So we have infinitely many planes passing through the line of intersection. Let us write the equation of all those planes. They form a family of planes. Let equation of pi 1 plane be vector r dot vector n1 is equal to d1 and equation of pi 2 plane be vector r dot vector n2 is equal to d2. Therefore, the equation of planes passing through the line of intersection of these two planes is vector r dot n1 plus lambda n2 is equal to d1 plus lambda d2. This is the formula. Let us write the corresponding Cartesian formula. Let the Cartesian equation of the first plane be a1x plus b1y plus c1z plus d1 is equal to 0. and equation of the second plane be a2x plus b2y plus c2z and plus d2 is equal to 0. The equation of the plane passing through the line of intersection is a1x plus b1y plus c1z plus d1 plus lambda times the second expression a2x plus b2y plus c2z plus d2 is equal to 0. I have written d1 and d2 on the left side of the equations so that I will have plus d1 and plus d2 in the formula. There won't be any confusion in the sign if you memorize the formulae with plus signs. So, for different values of lambda, we will get different members of this family. We have infinitely many planes passing through the line of intersection. Memorize these two formulae. Now, we will do questions finding the equation of such planes. Exercise 11.3, question number 9. Find the equation of the plane through the intersection of the planes 3x minus y plus 2z minus 4 is equal to 0 and x plus y plus z minus 2 is equal to 0 and the point 2, 2, 1. So, this 2, 2, 1 point is given to find one member of that whole family. Let us write the Cartesian formula a1x plus b1y plus c1z plus d1 plus lambda times a2x plus b2y plus c2z plus d2 is equal to 0. Let us write the first expression from the first plane equation 3x minus y plus 2z minus 4 plus lambda times the second expression x plus y plus z minus 2 is equal to 0. If the constant terms are given on the right hand side of the equations, bring them to the left hand side and substitute. Let us rearrange the terms. We will write x terms together and then y terms minus 1 plus lambda times y and then z terms 2 plus lambda times z minus 4 minus 2 lambda is equal to 0. This equation represents infinitely many planes, but we need one member from this whole family which passes through the point 2, 2, 1. Let us substitute the point 2, 2, 1 to find the corresponding value of lambda. 3 plus lambda times 2 minus 1 plus lambda times 2, y coordinate is also 2, 2 plus lambda into 1 minus 4 minus 2 lambda is equal to 0. Let us open the brackets. 6 plus 2 lambda minus 2 plus 2 lambda plus 2 plus lambda minus 4 minus 2 lambda is equal to 0. These two are getting cancelled. So, we get 3 lambda plus 2 is equal to 0. Therefore, lambda is minus 2 divided by 3. Now, let us substitute this value of lambda in equation number 1. Therefore, equation 1 becomes 3x minus y plus 2z minus 4 plus lambda times, lambda is minus 2 divided by 3 times x plus y plus z minus 2 is equal to 0. Let us multiply the equation by 3. We get 3 times 3x minus y plus 2z minus 4 and minus 2 times x plus y plus z minus 2 is equal to 0. It will be easy for us to solve by substituting in equation 1 than substituting in the next step. Open the brackets. 9x minus 3y plus 6z minus 12 minus 2x minus 2y minus 2z plus 4 is equal to 0? The answer is 7x minus 5y plus 4z minus 8 is equal to 0. This is the equation of the plane passing through the line of intersection of the given two planes, and this plane passes through the point 2, 2, 1. Question number 10. Find the vector equation of the plane passing through the intersection of the planes vector r dot 2i cap plus 2j cap minus 3k cap is equal to 7 and vector r dot 2i cap plus 5j cap plus 3k cap is equal to 9. And through the point 2, 1 and 3. It is same as question 9, but here vector equations are given. Let us write the vector equation passing through the line of intersection of the given two planes. R dot vector n1 plus lambda times vector n2 is equal to d1 plus lambda d2. In this vector formula, we have written the constant terms on the right hand side. So in the equations also, we take them to the right hand side and substitute in the formula. In this question, the constant terms are on the right hand side. Vector r dot n1 vector. From the first plane equation, it is 2i plus 2j minus 3k plus lambda times, and n vector of the second plane is 2i plus 5j plus 3k equal to, constant terms are on the right hand side, no problem here, 7 plus 9 lambda. Let us rearrange the terms. Vector r dot, let us write I components together, 2 plus 2 lambda times I cap. Now j components, 2 plus 5 lambda j cap and minus 3 plus 3 lambda k cap is equal to 7 plus 9 lambda. Now to find the value of lambda, the condition given is the plane passes through 2, 1, 3. So let us substitute the point 2, 1, 3. Substitute a point means we substitute for x, y, z in the Cartesian equation. In vector equation, for vector r we have to substitute because vector r is xi plus yj plus zk. So we have to substitute for vector r. 2i plus 1j plus 3k dot 2 plus 2 lambda I plus 2 plus 5 lambda j and minus 3 plus 3 lambda k is equal to 7 plus 9 lambda. Let us do the dot product. Corresponding components should be multiplied. 2 times 2 plus 2 lambda plus 1 into 2 plus 5 lambda and plus 3 times minus 3 plus 3 lambda is equal to 7 plus 9 lambda. Let us open the brackets. 4 plus 4 lambda plus 2 plus 5 lambda minus 9 plus 9 lambda is equal to 7 plus 9 lambda. 9 lambda is getting cancelled. We get 9 lambda. 6 minus 9 is minus 3 is equal to 7. Therefore, lambda is equal to 10 divided by 9. Substitute it in the first equation. Therefore, the equation of the plane is r dot 2i cap plus 2j cap minus 3k cap plus lambda is 10 divided by 9 times 2i plus 5j plus 3k equal to, substitute lambda value on the other side also. So 9 times 10 by 9, which is 17. Let us multiply the equation by 9. So you have to multiply throughout by 9. So here we will get 9, here 9 will get cancelled, here it will become 17 times 9. Vector r dot 18i plus 18j minus 27k, and here multiply by 10, 20i plus 50j plus 30k is equal to 153. Vector r dot 18i plus 20i is 38i plus 68j plus 3k is equal to 153. This is the answer. 11th question. Find the equation of the plane through the line of intersection of the planes x plus y plus z is equal to 1 and 2x plus 3y plus 4z is equal to 5, which is perpendicular to the plane x minus y plus z is equal to 0. We will write the equation of the whole family. The formula is a1x plus b1y plus c1z plus d1 plus lambda times a2x plus b2y plus c2z plus d2 is equal to 0. We will substitute. The first equation is x plus y plus z. Bring that constant term to this side, minus 1 plus lambda times 2x plus 3y plus 4z minus 5 equal to 0, because we have written d1 and d2 on the left side. So, take them to the left side and substitute in the formula. Let us rearrange the terms. X terms together, 1 plus 2 lambda times x plus 1 plus 3 lambda times y plus 1 plus 4 lambda times z minus 1 minus 5 lambda equal to 0. Now, to find the value of lambda, the condition given is x minus y plus z is equal to 0 is perpendicular to this plane. So, the perpendicular plane is x minus y plus z is equal to 0. If two planes are perpendicular, their normals are also perpendicular. Consider these two perpendicular planes. Their normals are also perpendicular. Let us write the normal of the first plane. The coefficients of x, y, z will give you the normal. 1 plus 2 lambda I cap plus 1 plus 3 lambda j cap plus 1 plus 4 lambda k cap. Let us write the normal of the perpendicular plane. The coefficients of x, y, z, 1i minus 1j and plus 1k. The condition is n1 dot n2 should be 0, because normals are also perpendicular. Dot product corresponding component should be multiplied and added. 1 into 1 plus 2 lambda minus 1 into 1 plus 3 lambda plus 1 into 1 plus 4 lambda equal to 0. So, 2 lambda minus 3 lambda plus 4 lambda will be 3 lambda, and 1 minus 1 are getting cancelled, equal to minus 1. Therefore, lambda is minus 1 divided by 3. Let us substitute the value of lambda in equation number 1. X plus y plus z minus 1 minus 1 by 3 times 2x plus 3y plus 4z minus 5 equal to 0. Let us multiply this equation by 3. we get 3 times x plus y plus z minus 1. 3 will get cancelled here. Minus of 2x plus 3y plus 4z minus 5 is equal to 0. Let us open the brackets. 3x plus 3y plus 3z minus 3. Distribute the minus sign. Minus 2x minus 3y minus 4z plus 5 is equal to 0. Therefore, the answer is x minus z plus 2 is equal to 0. Let us learn the formula to check the coplanarity of two lines. Coplanar lines means they lie on the same plane. Let us consider two line equations. Vector r is equal to a1 plus lambda times b1 and vector r is equal to a2 plus mu b2. Given two lines, they may be parallel or they may intersect each other at a point, or they may be skew lines. In these two cases, the lines are coplanar. But if the lines are skew lines, they are non-coplanar. So, coplanarity of two lines we can check by B1 parallel to B2. So, if these two vectors are parallel, the lines are parallel, therefore, they are coplanar, we can conclude. Now, we have to check whether the lines are intersecting lines or skew lines. So, we can check by shortest distance. So, it is enough if you calculate the numerator of the shortest distance formula, which is a2 minus a1 dot b1 cross b2. If this is 0, shortest distance is 0. That means the lines are intersecting each other, therefore, they are coplanar. If this is not 0, they are skew lines, therefore, they are non-coplanar. And the Cartesian form of this equation is a2 minus a1. This is a scalar triple product. We can write it as a determinant. a2 minus a1 is x2 minus x1, y2 minus y1, z2 minus z1, and components of b1 vector we will take them as a1, b1, c1, and components of b2 vector be a2, b2, c2. So, this determinant value has to be 0. This is the coplanarity condition for two given lines. Let us learn the formula to find the angle between two planes. Consider these two planes and let the equation of these two planes be vector r dot vector n1 is equal to d1 and vector r dot vector n2 is equal to d2. This is the normal of the first plane, which is vector n1. This is normal of the second plane, which is vector n2. An angle between the planes is theta. These two angles are 90. Fourth angle will be 180 minus theta. Therefore, this angle will be theta. Angle between two planes is equal to angle between their normals. So, we will find the angle between their normals. Cos theta is equal to vector n1 dot vector n2 divided by magnitude of vector n1 times magnitude of n2 vector. And to get the acute angle between the planes, we can write absolute value sign. This is the vector formula to find the angle between two planes. Let us consider the Cartesian equations of these planes as a1x plus b1y plus c1z plus d1 is equal to 0, and the second plane equation be a2x plus b2y plus c2z plus d2 is equal to 0. drs of vector n1 are the coefficients of xyz terms a1, b1, c1, and drs of normal to the second plane, the coefficients of xyz are a2, b2 and c2. Cos theta formula will be, let us find the dot product. It is a1 a2 plus b1 b2 plus c1 c2. Absolute value sign is there to get the acute angle between them, divided by root of a1 square plus b1 square plus c1 square times the root of a2 square plus b2 square plus c2 square. This is the corresponding Cartesian formula to find the angle between two planes. If these two planes are perpendicular, then normals will be perpendicular to each other, and perpendicularity condition is dot product has to be 0. Therefore, a1 a2 plus b1 b2 plus c1 c2 will be 0. Now, case 2, let the planes be parallel to each other. So, in that case, vector n1 will be parallel to vector n2. So, the parallel condition of two vectors is the proportionality. Therefore, a1 divided by a2 is equal to b1 divided by b2 is equal to c1 divided by c2. Next, let us learn the formula to find the distance of a point from a plane. Consider a plane. Let P be a point whose position vector is vector A. We need to find the perpendicular distance between P and the plane. Let us consider an arbitrary point on the plane whose position vector is vector R. Let us join P and this point, and foot of the perpendicular be L. Let us join LA. Vector PA is vector R minus vector A, where position vector of the point P is vector A, and we can take normal of the plane along PL. Let the equation of the plane be vector R dot vector n is equal to D. Now, the distance PL, that is the distance of a point from a plane, that is nothing but projection of vector R minus vector A on vector n. We know the projection formula. It is R minus A dot vector n divided by magnitude of vector n. Distance is a positive quantity, so we will take the absolute value sign. Let us distribute this dot product. We get vector R dot vector n minus vector A dot vector n divided by magnitude of vector n. And the equation of the plane is R dot n is equal to D. Therefore, we can substitute R dot n as D. Absolute value of D minus vector A dot vector n divided by magnitude of vector n. We have absolute value sign, so we can change and write it as absolute value of vector A dot vector n minus D. Because of the absolute value sign, it does not matter, divided by magnitude of vector n. This is the formula to calculate the perpendicular distance between a point and a plane. Let us write the corresponding Cartesian formula. Let the Cartesian equation of the plane be Ax plus By plus Cz plus D equal to 0, and let the point P be x1, y1 and z1. Therefore, the Cartesian equation becomes ax1 plus by1 plus cz1 plus d. It can be written as plus d or minus d. Plus d is better. There won't be any confusion in the sign. Divided by magnitude of the normal vector, the coefficients of x, y, z, root of a square plus b square plus c square, and distance has to be positive, so absolute value sign. And this is the Cartesian formula to find the distance between a point and a plane. Now let us write the formula to find the distance of a plane from the origin. So that will be distance OL. P point is the origin in this case. Vector A will be a 0 vector. So the first term becomes 0. We get modulus of d divided by magnitude of vector n. In this formula, A is 0. So the first term becomes 0. This is the vector formula and the Cartesian formula. Here this P point will become 0, 0, 0. Therefore, these first three terms will be zeros. We get absolute value of d divided by the magnitude of normal vector is root of a square plus b square plus c square. This is the formula to find the distance between the origin and the plane. Distance means perpendicular distance between them. Next formula, angle between a line and a plane. Let us consider a plane and a line intersecting the plane. We are going to find the angle between the line and the plane. This is b vector, and let us draw normal to the plane. This is vector n. This is 90 degrees. Therefore, this angle will be 90 minus theta. 90 minus theta is the angle between vector b and vector n. Therefore, cos of 90 minus theta is vector b dot vector n divided by magnitude of vector b times magnitude of vector n, and we will find the acute angle between them, so absolute value of. But cos of 90 minus theta is sin theta. Vector b dot vector n divided by magnitude of vector b times magnitude of vector n, an absolute value sign for the numerator to give the acute angle between them. This is the formula to find the angle between line and a plane. Only this formula has sin theta. All other angle formulae have cos theta. Question number 12 of exercise 11.3. Find the angle between the planes whose vector equations are vector r dot 2i plus 2j minus 3k is equal to 5 and vector r dot 3i minus 3j plus 5k is equal to 3. Angle between two planes is same as angle between their normals. Cos theta is equal to, the formula is vector n1 dot vector n2 divided by magnitude of vector n1 times magnitude of vector n2, and we can give the acute angle between them, so absolute value sign in the numerator, where vector n1 is 2i plus 2j minus 3k and vector n2 is 3i minus 3j plus 5k, and dot product, multiply the corresponding components. 2 3s are 6 minus 2 3s are 6 minus 15 divided by magnitude of the first normal 2 square plus 2 square plus minus 3 the whole square times magnitude of the second vector root of 3 square plus minus 3 the whole square, which is 9, plus 5 square 25. The answer is 15 divided by root 17 times root 43, and 43 times 17. So 15 divided by root of 731. Therefore, theta is equal to cos inverse of 15 divided by root of 731. Question number 13. In the following cases, determine whether the given planes are parallel or perpendicular, and in case they are neither, find the angles between them. The first subdivision, the planes are 7x plus 5y plus 6z plus 30 is equal to 0 and 3x minus y minus 10z plus 4 is equal to 0. DRs of normal of the first plane are 7, 5, 6, the coefficients of x, y, z, and DRs of normal of the second plane 3, minus 1, minus 10. They are not proportional, therefore they are not parallel. Let us check the dot product. Perpendicularity condition we are checking. 21 minus 5 minus 60, not 0. So they are neither parallel nor perpendicular. In such cases, we have to find the angle between them. Therefore, cos theta is equal to, the formula is n1 dot n2, absolute value of, divided by magnitude of n1 times magnitude of n2. Dot product just now we calculated 21 minus 65, which is minus 44, divided by magnitude of the first vector, root of 49 plus 25 plus 36 times magnitude of the second vector, 9 plus 1 plus 100, which is 44 divided by root of, the first total is 110 and the next one is 110. 44 divided by 110, we can cancel 11 and 2. So the answer is 2 divided by 5. Therefore, theta is equal to cos inverse of 2 divided by 5. This is the angle between the two given planes. Now B subdivision. The planes are 2x plus y plus 3z minus 2 is equal to 0 and x minus 2y plus 5 is equal to 0. The DRs of the normal 2, 1, 3 and DRs of normal of the second plane 1, minus 2, 0. There is no z term. They are not parallel because they are not proportional. Let us find the dot product to check whether they are perpendicular or not. Yeah, we get 0. That means the planes are perpendicular. C subdivision. The plane equations are 2x minus 2y plus 4z plus 5 equal to 0 and 3x minus 3y plus 6z minus 1 is equal to 0. DRs of n1 vector 2, minus 2 and 4 and DRs of n2 vector 3, minus 3 and 6. Let us check the proportionality. They are all proportional. We get 2 by 3. Therefore, n1 is parallel to n2, which implies planes are parallel. D subdivision. The equations are 2x minus y plus 3z minus 1 is equal to 0 and 2x minus y plus 3z plus 3 is equal to 0. DRs of vector n1 2, minus 1, 3, Let us write drs of the second one. n2 vector 2, -1 and 3. They are same. That means n1 parallel to n2. Therefore, the planes are parallel. By E subdivision, the equations are 4x plus 8y plus z minus 8 is equal to 0 and y plus z minus 4 is equal to 0. Let us write drs of n1, 4, 8 and 1. From the second plane equation, drs of n2. There is no x term, so 0, 1 and 1. They are not proportional. Even dot product is not 0. So, neither parallel nor perpendicular. In such cases, we have to find the angle between them. Cos theta formula is absolute value of vector n1 dot vector n2 divided by magnitude of n1 times magnitude of n2. Absolute value of 0 plus 8 plus 1 divided by magnitude of the first vector 4 square plus 8 square plus 1 square, root of 0 square plus 1 square plus 1 square, 9 divided by root of 81 times root 2. Root 81 is 9. The answer is 1 by root 2. Therefore, theta is pi by 4. Question number 14. In the following cases, find the distance of each of the given points from the corresponding given plane. The first subdivision, the point given is the origin and the plane equation is 3x minus 4y plus 12z is equal to 3. Distance from the origin. The formula is absolute value of d divided by root of a square plus b square plus c square, which is equal to absolute value of d is 3 divided by root of 3 square plus minus 4 square plus 12 square. 3 can be kept on that side or on this side. Whether you write absolute value of minus 3 or plus 3, it is the same. 3 divided by this total is 169. Root of 169 is 13. Therefore, the distance is 3 divided by 13 units. B subdivision. The point is 3 minus 2 and 1 and the plane equation is 2x minus y plus 2z plus 3 is equal to 0. So, the distance formula is, that is distance of a plane from a point. The formula is ax1 plus by1 plus cz1 plus d divided by root of a square plus b square plus c square, and we have absolute value sign because distance cannot be negative. Let us substitute this point in the plane equation, that is the numerator. 2 times 3, 6, minus of minus 2 plus 2, 2 times 1 and plus 3 divided by root of drs of normal are 2 minus 1, 2, the coefficients of x, y, z. So, 2 square plus minus 1 the whole square plus 2 square, and we have absolute value sign. So, it is 13 divided by 3 units. C subdivision, the point is 2, 3 minus 5 and the equation is x plus 2y minus 2z is equal to 9. So, same formula, that is distance of the plane from the origin is ax1 plus by1 plus cz1 plus d divided by root of a square plus b square plus c square. Distance has to be positive, so don't forget to write the absolute value sign, which is equal to, substitute the given point in the plane equation. That is the numerator. So x is 2, y is 3, 2 3s are 6, minus 2 into minus 5 is plus 10. Bring that constant term to this side, minus 9, divided by root of normal, the coefficients of x, y, z, 1, 2, minus 2. So 1 square plus 2 square plus minus 2 the whole square is 4. The numerator is 9, divided by denominator is root of 9, which is 3. The answer is 3 units. D subdivision. The point is minus 6, 0, 0, and the plane equation is 2x minus 3y plus 6z minus 2 is equal to 0. Let us write the formula. Distance of a plane from the given point. Absolute value of a x1 plus b y1 plus c z1 plus d divided by root of a square plus b square plus c square. Substitute the point in the plane equation. I told you that is the numerator. So 2 times minus 6, minus 12, y is 0, z is 0, constant term is minus 2. And we have absolute value sign because distance has to be positive, divided by the drs of normal are the coefficients of x, y, z, which are 2, minus 3 and 6. So the denominator is root of 2 square plus minus 3 the whole square is 9 plus 6 square is 36. The numerator becomes plus 14 divided by root 49, which is 7. 14 divided by 7 is 2 units.